Prepare to have your understanding of reality completely shattered. What if everything you thought you knew about computers, about information, about the very fabric of existence was just wrong? We're about to dive into quantum computing, a technology so bizarre, it makes science fiction look mundane and your current tech look like a fancy rock. Your laptop is a potato. A very, very dumb potato. You think you know computers, right? You've got your fancy laptop, your smartphone that knows more about your questionable late-night snack choices than you do. You're living in the digital age, bytes and bits flying around, making the world go round. And bless your heart, that's adorable. Because what you're interacting with, that's a glorified abacus, a very fast, very well-organized, but ultimately dumb abacus. Your computer, bless its metallic little heart, is a binary beast. It understands two things, on or off, yes or no, 1 or 0. It's like asking a librarian to find you a book, and they have to check every single shelf one by one, deciding, is this the book, or is this not the book? It's incredibly efficient for what it does, but it's also incredibly rigid, limited. But what if I told you there's a whole other dimension of computing out there? A realm where particles don't play by the rules, where logic takes a holiday, and where the very fabric of reality gets a little squishy. We're talking about quantum computing. And let me tell you, it's like your orderly librarian suddenly decided to throw a multi-dimensional rave in an ice cave. And everyone's invited, including the particles that aren't quite sure where they are. This isn't just a bigger, faster laptop. Oh no, this is the equivalent of upgrading from a horse and buggy to a teleportation device that occasionally sends you to a parallel universe where socks are currency. It's weird, it's wonderful, and it's going to make your current tech look like a set of really fancy rocks. Meet the qubit, the particle who can't make up its mind, and that's a good thing. So your classic computer uses bits. Simple, elegant, utterly decisive. A bit is either a 0 or a 1. Like a light switch, it's either off or it's on. No, maybe kinda on, or a little bit off. Very clear boundaries. But in the quantum realm, we don't have bits. We have qubits. And a qubit is the ultimate indecisive teenager. It can be a 0, it can be a 1, or, and this is where it gets spicy, it can be both at the same time. This mind-bending state is called superposition. Picture this. You flip a coin. While it's spinning in the air, it's neither heads nor tails, right? It's in a state of glorious uncertainty. It's both, and neither, until it slaps down on the table. A qubit is like that spinning coin, but it stays spinning until you force it to land. It holds all possible outcomes simultaneously. This means, instead of checking one answer at a time, a quantum computer can explore all potential answers at once. It's like having a million librarians checking a million different books simultaneously, instead of just one librarian checking one book at a time. The sheer parallelism is astounding. And then, just when you thought it couldn't get any weirder, we introduce entanglement. Imagine two qubits are like cosmic best friends who are so deeply connected they literally share a single destiny. You mess with one, the other instantly knows, no matter how far apart they are. It's like having a pair of socks, where if one sock decides to be red, the other sock instantly, magically, becomes blue, even if it's in a different galaxy. And you didn't even touch the second sock. This isn't communication, mind you. It's not sending a signal. It's more like they're two sides of the same cosmic coin. Measure one, and you instantaneously know the state of the other. Einstein called it spooky action at a distance, and frankly, he wasn't wrong. This bizarre connection allows quantum computers to perform computations that are literally impossible for classical machines because they can correlate information across vast numbers of entangled qubits in ways that would make your head spin faster than a superposed electron. And just for a bonus round of physics is having a laugh, let's talk about quantum tunneling. Sometimes a quantum particle just decides it doesn't feel like being stopped by a wall. It just appears on the other side. Like you deciding you don't want to use the door, so you just phase through the wall into the next room. Don't try this at home, unless your home is a quantum lab and you're a subatomic particle having an existential crisis. This isn't directly part of how we compute with qubits. but it's another example of the sheer, unbridled chaos that these tiny things embody, and it underscores just how different this world is. The quantum playground, where logic goes to die and problems get solved. So, you've got these qubits, capable of existing in multiple states at once and entangled with their buddies across the digital cosmos. How do we actually use this cosmic weirdness? We build a quantum computer. And let me tell you, it's not a desktop tower. It's a colossal cryogenic chandelier that looks like it just landed from the future to judge your life choices. The biggest challenge? Keeping these finicky little quantum divas stable. Qubits are like the most sensitive, high-maintenance celebrities you can imagine. Any stray photon, any tiny vibration, any whisper of a cosmic ray, and they decohere. They lose their superposition, their entanglement, and collapse into boring, predictable zeros or ones, just like your dumb classical bits. Poof! All that quantum magic? Gone. It's like trying to keep a dozen sugar-fueled toddlers perfectly still in a room full of bouncy castles. Impossible! So to get these things to work, we have to isolate them from literally everything. And I mean everything. Let's count the ways the universe tries to ruin our quantum fun. Threat number 1, temperature. These things have to be colder than deep space. We're talking millikelvins, like negative 459 degrees Fahrenheit, colder than your ex's heart, colder than the vacuum of space itself. If it gets even a smidgen warmer, those delicate quantum states just evaporate. Threat number 2, vibrations. Any tiny tremor, any seismic activity, even the distant rumble of a truck on the street outside can wreak havoc. It's like trying to perform brain surgery during an earthquake. We're talking about isolating them from the very vibrations of the Earth. Threat number 3, electromagnetic noise. Every radio wave, every Wi-Fi signal, every flicker of light is a chaotic sledgehammer to a qubit. They need to be in a pristine, electromagnetically silent environment. It's like trying to have a quiet conversation in the middle of a heavy metal concert. Threat number 4, cosmic rays. And if all that wasn't enough, you've got high-energy particles from space constantly zipping through everything. These things are basically tiny, invisible bullets for qubits. We're fighting the universe, one particle at a time. So why bother with all this cosmic babysitting? Because when you do get them to work, even for a fleeting moment, they can solve problems that are currently impossible for even the biggest supercomputers. We're talking about drug discovery, simulating how molecules twist and fold, finding new medicines. Your current computer can barely model a few atoms. A quantum computer can potentially model entire proteins, accelerating breakthroughs by decades. Materials science, designing new materials with properties we can only dream of. Imagine superconductors that work at room temperature, or super-efficient batteries. Financial modeling, predicting stock market fluctuations, optimizing complex financial strategies. It's like having a crystal ball that actually works, instead of just showing you static. And, perhaps most famously, breaking encryption. The very encryption that secures your online banking, your emails, your secret obsession with cat videos, a powerful quantum computer could potentially crack it in minutes. Which is why everyone's scrambling to develop quantum-resistant encryption. Don't panic just yet. These machines aren't quite there. The current quantum supremacy moments you hear about? They're not about beating classical computers at everything. They're about beating them at one specific, incredibly niche, often pointless task. Like generating truly random numbers, or solving a very particular mathematical problem that has no real-world application, but proves the quantum computer can do something a classical one simply cannot. It's like a super genius who can only tie their shoes in 17 dimensions while reciting the entire works of Shakespeare backward. Impressive, but not yet practical for your daily commute. So we're all quantum, now what? So there you have it, quantum computing. It's not magic, it's just physics being aggressively weird. It's a universe of particles that can't make up their minds, that are inexplicably linked across vast distances, and that require more pampering than a newborn royal. It's not going to replace your laptop for Netflix or email. It's a tool for the truly impossible problems, the ones that require peering into the very fabric of reality to unravel. We're only just beginning to scratch the surface of what these machines can do, and the challenges of building them are immense. But it's a glimpse into a future where our understanding of information, and indeed reality itself, gets a serious, mind-bending upgrade. So enjoy your simple, binary existence for now. The quantum realm is coming, and it's bringing all its delightful, indecisive chaos with it. You're welcome. Or perhaps, I'm sorry,